Hello, I'm Ezra. This is AP Calculus A, B, and BC Review, Unit 5, Analytical Applications of Derivatives. So, in this unit, we focus more so on graphs and functions rather than real-world applications. So we take a look at what critical points are, how to find increasing and decreasing intervals, as well as minimums and maximums. We look at the extreme value theorem, and then finally we define concavity and look at points of inflection. So let's get started. So, what is a critical point? Well, a critical point is essentially just when the derivative of a function equals 0. And this goes for anything. So, let's just take the function x squared plus 1, right? Gonna look exactly like this. So, when you take the derivative of this, you will get 2x, and then you set it equal to 0, and this is how you find your critical points. All you do is you take the derivative of your function and set it equal to 0. In this case, the critical point is at x equals 0, which is right here. Now, something that you may notice about this is the vertex of this function, right at the absolute minimum of this function, but also it is when the function goes from decreasing to increasing. So, before this point, you go from negative infinity all the way up here, and you're decreasing down until you hit this point, and then you begin increasing back up. So, we can actually define these intervals using critical points. So, when you find the critical point of a function, in this case only x equals 0, you should usually make what is called a sign chart, which is essentially a number line where you mark your critical points, and then you can test to see whether the derivative is positive or negative on either interval adjacent to that critical point. So, if you think about it, the derivative is the slope of the function. So, when the derivative is negative, that means the slope of the function is negative, so the function is decreasing. And then vice versa, when the derivative is positive, the slope is positive, so the function is increasing. So in this case, we have our derivative right here, 2x. When x is less than 0, you plug in a test number. So let's plug in -1. 2 times -1 is -2. So this means that because this is the only critical point, when x is less than 0, it's going to be negative across the whole interval all the way to infinity. And then the same thing to the right, you plug in a test interval. Let's plug in 1, and that gives us 2. That means it's going to be positive on this interval to the right of 0. So, if you were asked to find the interval in which it is increasing, you would say it is increasing on 0 to infinity. Or you can write x is greater than 0. And then it's decreasing for x is less than 0. So, let's take a little more complicated function than that. Let's take 1/3 x cubed minus 3x squared plus 8x. So, we have f of x here. So our derivative is going to be x squared minus 6x plus 8. And then we set that equals 0. These are our critical points. Equals, I'm going to factor it right here. This is the same as this. And then we find our critical points are at x equals 4, x equals 2. So let's create our number line here, our sign chart with 2 on it and 4 on it. Now let's test the derivative. When you plug in a number less than 2, let's plug in 0 to make it easy. We'll have 0 minus 4, 0 minus 2, which is negative 4 times negative 2, which is 8. That is a positive number, which means that when x is less than 2, the derivative is positive, so the function is increasing. Okay, now what about between 2 and 4? Well, there's one number that's pretty easy between 2 and 4, and that's 3. So 3 minus 4 times 3 minus 2 is negative 1 times 1, or negative 1. And now that's negative. So between 2 and 4, it is decreasing. Okay. And then x is greater than 4. You plug 5 in, for instance. 5 minus 4 times 5 minus 2 is just going to be 3. So positive. Thus, our function is increasing from x is less than 2 and x is greater than 4, and it is decreasing from x is between 2 and 4, which you would write as x is less, or 2 is less than x, which is less than 4. Okay. One more I'm going to show is a function x to the 4th plus 2x squared. So, take the derivative, 4x cubed plus 4x. Factor out this, x squared plus 1. Okay, so here, our only 0 is x equals 0. So let's try. When x is less than 0, we're going to have whatever number. Let's try negative 1. You have negative 4, and then negative 1 squared is 1 plus 1 is 2. That's going to be negative. Okay. And then if you try a positive number, 1, 4 times 1 plus 1 is 2. So 4 times 2 is 8. And that's going to be positive. So this would be our sign chart for this function. Now, these sign charts can also be used to find relative minimums and maximums. So what is a relative minimum and maximum? Well, if you take a function like this, right? Your relative maximums are just going to be the peaks that it hits. So right here, right here, right here, and then your relative minimums are going to be the divots. So right here, and then right here. Now, what you'll notice about the lines that I drew is that on this function, you have these horizontal tangents, which is when the derivative equals 0, at all of these relative minimums and maximums. So, every relative minimum and maximum is a critical point. So let's take this function that we had again. 1/3 x cubed minus 3x squared plus 8x. Once you take the derivative of it, we had our x squared minus 6x plus 8. And then, if you remember, we had our sign chart. 2, 4, positive, negative, positive. So, how do we find our relative minimums and maximums from this sign chart? So remember, this is when the derivative is positive and negative. So, if you think about how the slope will look at a maximum or minimum, I'm just going to draw this right here. At a maximum, the slope is positive, 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 and then it hits 0 at the maximum, and then it turns negative. And then, for the minimum, it's negative, 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 it hits 0, and then it turns positive and starts increasing, the graph of the function. So, if you look at a sign chart that you created for the derivative, it's positive over here, and then we know that the derivative is 0 at these critical points. So, if it's positive, 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 and then it hits 0 and then goes negative, 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 this is our relative maximum. And then, the same can be said vice versa for this. It's negative over here, so the derivative is negative, it's decreasing, decreasing, hits 0, then starts increasing. That means this is our relative minimum. So, relative maximums occur when the derivative goes from positive to negative, and then relative minimums occur when the derivative goes from negative to positive. Now, if I were to give you the sign chart of some arbitrary function like this, this is still a critical point. Even though the sign of the derivative doesn't change, it's still, hypothetically speaking, equals 0 at x equals 3. This is important to note for later, because this relationship is not true for concavity. But we'll talk about that in a little. So, here you have a minimum, right, at x equals 1. And then at x equals 3, you don't have a minimum or a maximum. You have neither. So if a question asks you, do you have a relative minimum, maximum, or neither at x equals 3? You say you have neither because f prime of x doesn't change signs. That is what you have to say. Now, if you have a relative minimum, you say you have a relative minimum because f prime of x goes from negative to positive at x equals whatever. And then, if you have a maximum, f prime of x goes from positive to negative at x equals whatever. Now, we're going to talk about extreme value theorem, or EVT. Value theorem. Alright, so this is basically stating, and this is arguably the simplest of the 3 theorems we've covered, IVT, MVT, and now EVT. This is saying that on any given interval, as long as it is continuous, you will always have an absolute minimum and an absolute maximum. So, how would you find these absolute minimums and maximums? So, if I gave you an interval, or not an interval, but a function over an interval, like this. Some really weird function. If you just look at the graph, the absolute minimum is clearly right here, because it's the lowest point, and the absolute maximum is right here. However, if this were a function and I gave you the critical points, you know, there's a lot over here, but if I gave you these critical points and you analyzed all of the critical points and you determined, okay, this one's the maximum, you would get the wrong answer. So, in order to determine absolute maximum, you have to not only consider the critical points, but also the endpoints. So, if you have whatever function this is, let's say this is at 0, this is at x equals 6, this is at x equals 4, this is at x equals 2. So, to find your absolute maximum and minimum, you look at f of 0, f of 2, f of 4, and f of 6. So, it will say that on the interval from 0 to 6, this function is defined as whatever. When you find the critical points of that function by setting the derivative equal to 0, you'll get 2 and 4. When you plug 2 and 4 back into the original function, you will get your minimums, relative minimums, and relative maximums. So here, let's say the f of 2 is 2 and f of 4 is 5. Okay. You can't say that this is the minimum or maximum because you also consider the endpoints. It says it's on the interval 0 to 6, so you also have to look at x equals 0 and x equals 6. In this case, x equals 0, let's say, is 7, and 6 is obviously 0. So, if you wanted to find absolute minimum, absolute maximum, you look at critical points and endpoints. I'm going to reiterate. So, how does this relate to EVT? Well, like I said before, EVT just proves that there is a maximum. So, you can just say that f of x is continuous. Therefore, by EVT, there exists a C value where, and now here, if it is an absolute maximum, you say where f of c is greater than or equal to f of x. A is less than c, less than b. So, if you wanted to say that there was an absolute minimum, f of c is not less than, or not greater than or equal to f of x, but less than or equal to f of x. So this makes sense because if you say you have a value, f of c is your absolute minimum, that means on the rest of the function, this is f of x is the function. F of c will be less than all values of f of x because it is the absolute minimum. And that is the same for the absolute maximum. This absolute maximum right here is greater than all other values of f of x on the interval. So that is EVT. It's just another theorem, and again, it relies on being continuous. So make sure you can prove the continuity. Finally, we're going to talk about concavity. So concavity is essentially how the graph looks. So if you have a graph like this, right? Concave down is an upside down U shape, and concave up is a right side up U shape. So if you wanted to say, oh, this graph is concave down in this area about, right? You don't really know the exact point. Somewhere around here, it changes from concave down, and then now, over here, it's concave up. So, how do we figure out when it is concave up or down? Well, concavity is the second derivative of x. So, when f double prime of x is greater than 0, and when f double prime of x is less than 0, here it is concave up, and here is concave down. So, if we wanted to look at that, you would need to find the quote-unquote critical points of the second derivative graph, which we call points of inflection. So, let's again take this function over here. 1/3 x cubed minus 3x squared plus 8x. Great function. So, first derivative, x squared minus 6x plus 8. Second derivative, 2x minus 6. So, that means that we set this equal to 0, and then x equals 3 when this equals 0. So this is our point of inflection. That means if we draw our graph, at x equals 3, it changes concavity. Now, how do we know what it changes from? Well, we make a sign chart for concavity, and then test this function. So, at x equals 4, it's going to be positive, because 4 times 2 is 8, minus 6 is 2. And then when x is less than 3, it's going to be negative. So, now we know at x equals 3, the function will go from concave down to concave up, right here. Now, let's look at something like x squared plus 1 again. This looks like it's just concave up the whole time. So, let's prove that. If f of x is x squared plus 1, that means the derivative is 2x, and then the derivative of 2x is 2. So, the f double prime of x is just 2. And since 2 is always positive, that means that it will always be concave up, which, as we can see by the graph, makes sense. It always has that upwards U shape. So, one more thing is that points of inflection differ from critical points with the fact that if I give you this is not a point of inflection. Even though I'm saying f double prime of x equals 0 at x equals 1. This is a sign chart for f double prime of x. At x equals 1, it does not change signs. It stays from positive and then it goes to positive. So it doesn't change signs and therefore is not a point of inflection. This is different from critical points, like I said before, because even if you have this as a critical point for f prime of x, this is still a critical point because f prime of x equals 0. It doesn't matter that the signs don't change. f prime of x equals 0, so it is a critical point. Now, concavity can also be used to find the relative minimum and maximum. So, think about it like this. If I give you some function and I say that there are critical points at 1, 2, and 4, right? And then I say that it is that f of x is concave up on x is less than 1.5 and concave down on x is greater than 1.5. Okay, so if we look at just the graph, x squared plus 1 again, just to demonstrate. This is concave up, and we have a critical point here. So, we don't need to know the actual value of that critical point. We don't need to know, like, the sign changes or anything. Because it is this U shape has that little minimum at the bottom at the critical point of this U shape. So, if you have a critical point, you can use concavity to determine whether it's a minimum or maximum. So, here, in this case, since x is less than 1.5, or x double prime, I should say, is less than 1.5. No, x is concave down on less than 1.5 and concave up on greater than 1.5. Then we can say that because x equals 1 is a critical point, and it is concave down because it's less than 1.5, it's going to look like this. Concave down and a critical point up here. You don't even need to know the signs of the derivative to figure out that this is a relative maximum. Now, for 2 and 4, we're saying it's concave up. So, at 2, it will look like this. And at 4, it will look like this. So this is a relative minimum. This is a relative minimum because it's concave up and a critical point. So that is important to note. On FRQs, you could be given concavity. You could be given what the critical points are and not be given a function. So from there, you have to figure out if it is concave up, concave down, and then you can determine if it's a minimum or maximum, or neither. I'll show you what neither looks like. So, we have this function 2x minus 1. Now, if we take the derivative once, you just get 2. So 2 indicates that this doesn't have any relative minimums or maximums because it's just 2. The slope is 2 of a linear function with slope 2. I mean, it makes sense. But then you take the derivative again and you get 0. That means that there's no concavity, which, again, also makes sense. It's a line. It doesn't have a U shape at all. So, in this case, you could say that it is always increasing because the slope is always 2. And you could say it has 0 points of inflection. That means it has no minimums, no maximums. 0 points of inflection either means that your sign chart for f prime of x looks something like this, or it just means that f double prime of x equals 0. So usually you can determine that if f double prime of x equals 0, it's going to be a linear function. Finally, I'm going to talk about tangent lines. So, tangent lines are over/under approximations depending on the concavity. So I'm talking about tangent line approximation here. So let's give a function here. If I asked you to write a tangent line at x equals -1 to approximate x equals -0.8, you would draw me a tangent line like this, and then find the value right here of -0.8. So this, as you can see, if you were to zoom in on this bump right here, this is 0.8, and then this is -1. This is an overestimation. And then if we look at this part here, this is 1, and then I'll say this is 1.2, and then you wanted to draw a tangent line here. Zoom in on that. That would be an underestimation. So the note that you should take and keep in your mind is that tangent line approximations are overestimations when the graph is concave down. And then underestimations when the graph is concave up. So, if it ever asks you, was this tangent line an over or under approximation, you would have to show that you looked at the second derivative and determined if it were concave up or concave down. So, final notes. Use critical points and sign charts. They are extremely important, and using sign charts shows your work very simply. If you showed that you made a sign chart and then showed that you plugged in intervals or plugged in test values in the intervals, that will show them 100% that you know what you're talking about, and you will get full credit. Remember that minimums are when it goes from positive to negative to positive, and maximums are when it goes from positive to negative. Concavity is the shape of the graph, whether it's like an up U or an upside down U. And this is determined by f double prime of x. Remember, points of inflection only exist at a sign change. So, quite often on MCQs, they will ask you which of the following must be true. Usually, a point of inflection existing is not going to be correct because they don't tell you that the sign changes. It can tell you that it equals 0, that f double prime of x equals 0 at that point, but if the sign doesn't change, it is not a point of inflection. And then you should also remember that tangent lines are over/under depending on concavity. And remember one more thing, which I should have put up here. Test critical points and endpoints for absolutes. absolute max slash min. So that is it for Unit 5, Analytical Applications of Derivatives. Thanks for watching.